Welcome to the second fundamental theorem of calculus. This applies to functions defined by integrals. So we have this function, capital F of x, that's defined as the integral from 1 to x, because it's defined by x, of f of t dt. Now this should look kind of familiar. It's kind of like the accumulation functions that we studied earlier. So how do we work with it when it's not a graph? All right, so let's start with f of t equals 4t minus t squared. Well, what would that make capital F? Well, that makes capital F of x equal to the integral from 1 to x of 4t minus t squared. And that's with respect to t. So what happens when I take that integral, the antiderivative? Well, that means I'm going to take, let's see, 4t, I'd raise it to t squared and divide by 2. Then this would be t cubed divided by 3. And we're going to evaluate that from 1 to x. So when I plug in x, I'm going to get 2x squared minus x cubed over 3 minus, plugging in 1, 2 times 1 squared minus 1 cubed over 3. So f of x equals 2x squared minus x cubed over 3 minus, let's see, that's 2 minus 1 over 3. So that'd be 6/3 minus 1/3, that's 5/3. Now what happens if I take the derivative of capital F? The derivative of capital F would be 4x minus x squared, and then that would go to 0. All right, so let's do the next one. What if little f of t was cosine? Well, capital F of x is the integral from 1 to x of cosine t dt. So we're going to take the antiderivative. And the antiderivative of cosine is sine, because the derivative of sine is cosine. And we're going to evaluate that from 1 to x. So we're going to have sine of x minus sine of 1 capital F of x equals sine of x. And then if I go over to the side, that's 0.841. Now, what happens if I take the derivative of that? I get sine x, and then this constant goes to 0. Let's look at a different one. We have capital F of x is defined as the integral from 1 to x squared of f of t dt. Ooh, that one's a little bit different, right? So, capital F of x is defined as the integral from 1 to x squared of t cubed, and that's defined with t. So we're going to take the antiderivative. And the antiderivative of t cubed is t to the 4th divided by 4. And we're going to evaluate that from 1 to x squared. So, let's see. When I plug in x squared, so it's going to be x squared to the 4th divided by 4 minus 1 to the 4th divided by 4. Oh, let's see, x squared to the 4th power. That's x to the 8th. Minus 1/4. Now let's see what happens if I take the derivative of this function that was defined by the integral. Power comes down, I'll get 2 x to the 7th and plus 0. Capital F of x is defined as the integral from 1 to x squared of, and I'm going to write that as 6t to the 1/2 dt. So we'll take the antiderivative. Let's add 1 to the exponent. So that'd be 3/2 divided by 3/2, which is the same as multiplying by the reciprocal. And we're going to evaluate it from 1 to x squared. So when I plug in x squared into that, let's see, 2/3 of 6 is 4. X squared to the 3/2 minus 4 times 1 to the 3/2. Well, let's see, x squared, power to a power, you multiply, so you'll just get 3. Minus 4. What happens if I take the derivative of that function that was defined by an integral? I get 12x squared. Was there a faster way to do it? Kind of looks like there is up here. Kind of iffy there. Well, there is a faster way. Let's go and look at the second fundamental theorem of calculus. This theorem states if capital F of x is defined as going from some number to some function of x of f of t dt, where a is any constant, staples, constant, then the second fundamental theorem says there's a shortcut. To take the derivative of this function that is defined by an integral, we could take f of g of x times the derivative of g of x. Well, let's see if that works. Let's copy what we had from the previous page. On the page numbers don't match. When we found f prime of the integral from 1 to x of 4t minus t squared, when we found the integral of that, it was 4x minus x squared. Let's see if that matches this rule. Well, the second fundamental theorem says that f prime equals, if I took this and plugged it in for each of the t's, times the derivative of that function. So that'd be 4x minus x squared times the derivative of g of x, which in this case would be 1. It worked. Let's try it on the next one. From the previous page, we had found f prime of x was cosine x. Already looking good. If I apply the second fundamental theorem of calculus, I would substitute the x in for the t, times the derivative of that function. So in this case, times 1. Aha! Worked again. Love shortcuts, huh? Ooh, this was the one that looks different. Lost you for a second there. So on this one, on the previous page, when we took the derivative, we got 2x to the 7th. That doesn't look like just plugging in for t. So let's see how it works with the second fundamental theorem of calculus. It says to take x squared and plug it in, so you'd have x squared to the 3rd times the derivative of g of x. So in this case, that'd be 2x. Well, that's x to the 6th times 2x. That's 2x to the 7th. They match. Last one. From the previous page, we got that the derivative of capital F of x was 12x squared. Let's see why that worked. If I use this new theorem of calculus, f prime of x equals 6 times the square root of x squared, and I'm going to take that times the derivative of x squared. So square root of x squared is just going to give me 6x times 2x, and I get 12x squared. That's a lot faster than the process we used on the first page. Let's try a couple more, but using the shortcut. Notice that it said that this could be any constant whatsoever, because when we took the derivative of any constant, it's 0. So that's awesome. That means we have a nice shortcut. Here's our g of x. It's going to get substituted in. So f prime is going to be the square root of 2 minus 2x squared times the derivative of g of x, so times 2. Well, I'm just going to move the 2 to the front so we don't get confused. 2 minus all of 2x squared is 4x squared. Quick, fast. Uh-oh. This one doesn't have it in the right order. It doesn't follow the pattern. So how could I change the order of my boundaries of the integrand? Well, if I do change those boundaries, remember it'll change the sign. So let's rewrite g of x as negative, flip the boundaries. Oh, this one I really wouldn't have wanted to do the long way. The derivative of capital G is negative e to the cosine of x squared times the derivative of x squared. Make that a little prettier. Negative 2x e to the cosine of x squared. Does it remind you kind of the chain rule? Just a little bit? Does me too. H of x. So we have the constant to a function. Perfect. So h prime of x equals, plug it in, so cosine of x squared times the derivative of cosine, which is negative sine x. So to make that look a little bit better, I'm going to write that as negative sine x cosine squared. How could this help us with a graph? Well, let's see. we have a function. This time it's not a capital, but it's still a function defined by an integral. And inside the integral, it has a different variable. So if I was finding f of 0, first, that means we're finding this when x is 0. So, well, let's plug in 0. So that's the integral from -4 to 2 times 0 of g of t dt. Oh, well, that's just the integral from -4 to 0 of g of t dt. That's the area under the curve from -4 to 0. So let's break this apart. That piece and that piece match, so they would add to be 0. This is 2 by 1, so 2 times 1, plus this is 1/4 of a circle, pi, the radius is 2, which gives me 2 plus, that's 4, 1/4 of that would be 1, so 2 plus pi. Find the value of f of 2. Well, that's easy. That means we're going to plug in 2 for x. So we're finding the integral from -4 to 2 times 2, well, we know that's 4, of g of t dt. So what if we were finding the area of the entire figure? Well, it's symmetrical, so this side has to be the same as that side, so that would be 2 of the 2 plus pi's, or 4 plus 2 pi. Ah, there's a derivative. The derivative of a function that's defined as an integral. F prime of 1. Well, first, we've got to remember what we're going to be doing. So we're going to use the second fundamental theorem. That says we need to take this function and plug it in. So we're going to have g of 2x times the derivative of that function. G of 2. Now we can plug in 1. F prime of 1 equals g of 2 times 1. Take that times 2. F prime of 1 equals g of 2 times 2. G of 2 is actually just the y value when x is 2, and that's 1. So 1 times 2, f prime of 1 is 2. Find the value of f prime of -2. Well, we already figured out that f prime was going to be g of 2x times 2. So when I plug in -2, I'll have g of -4 times 2. Well, g of -4 is the y value that's associated with -4. That's -1 times 2. F prime of -2 is -2. Ooh, f double prime. Ooh, this is fun. So, f double prime. Well, we know that f prime was this function. I'm going to rewrite it a little bit. F prime of x would be 2 times g of 2x. Just move the 2 in front. That's a composite function. I can't talk today. So if I took the derivative of that, it'd be 2 times, when I take the derivative of a composite function, I'm going to take the derivative times the derivative of the inside, which gives me 4g prime of 2x. So what happens when I plug in 2? All right. That's 4 times g prime of 2 times 2, 4 times g prime of 4. So we want to know the derivative of g at 4. That's the slope at 4. Hold on just a second. So can we find the slope at 4? I can find the slope here. I can find the derivative there. That's 0. Not there, and definitely not there because it's an endpoint. So f double prime of 2 is undefined. Because g prime of 4 does not exist. I can't find the derivative at that endpoint. And the reason we can't do that is g of t is not continuous at x equals 4. It just stops there. Or at t, oh, I'm sorry, that was t. Let's do another example. All right, so the graph we're shown is f of t, and we have this function g, which is defined as an integral from -1 to x, good order, of f of t dt. Now remember, this is actually the accumulation function of the area under the curve from -1 to any value of x. It's technically what it is. G of -6 would be -1 to -6 f of t dt. Now notice that those boundaries are backwards. So that means we're really finding the opposite of -6 to -1 f of t dt. So let's see. -6, we've got, let's see, that's 2 by 4, be 8, half of that is 4. This little triangle would be a 1. This little rectangle, oh wait, I'm going only to -1. That's a 2 by 2, that's 4. So we have 4, and that'd be a -5. And we're taking the opposite of that. So 4 minus 5 would be a -1, but the opposite would be 1. So g of -6 is 1. G of +6. Ooh, okay, good. G of +6 would be the integral from -1 to +6 f of t dt. So from -1 to +6, we've got a quarter of a circle. We've got a rectangle. So let's see. Oh, that's all below the graph. So that's a -2 by 3. And then a -2 plus a quarter of a circle with a radius of 2. So I end up with -8 plus pi. The integral, and the derivative of this function defined by an integral. That would mean, we're going to go back up here, we're going to take the derivative of this integral. That means we're going to plug in x times the derivative of x. So f of x times 1. It's easy. G prime of 6 is f of 6. That means we're finding, since this f is this graph, we're finding the y value when x is 6. It's 2. G prime of 2 is going to be the output when x is 2. That's -2. G double prime of 2. Okay. So g prime was f of x. So g double prime is going to be f prime of x times the derivative of the inside, which is 1. So g double prime evaluated at 2 is going to be the slope of the graph when x is 2. So let's look. When x is 2, we have a sharp turn, a cusp. So this is undefined. Why? Because f of t has a sharp turn or a cusp at t equals 2. What about g double prime of negative 4? That would be f prime at negative 4. So let's see there. Okay, when x is negative 4, I like that. The slope down to over 1. Because the slope of f of t at t equals negative 4 is negative 2. Last example. And you're welcome to pause the video, go ahead and try this one on your own, then come back and check it if you're bold. This one's very interesting. G of 3. Now notice this one has an integral and a regular part. So g of 3 just means to plug in 3 for all the x's. So 1/2 3 squared plus the integral from 0 to 3 of f of t dt. And we are given the graph of f of t. So we need to find the area under the curve from 0 to 3. See, that would be 3, 1.5. Wait, those are exactly the same. So this would be half of 9, which would be 9/2, plus 0, so just 9/2. G of negative 4 means to plug in negative 4 for the x's. So 1/2 negative 4 squared plus the integral from 0 to negative 4 f of t dt. Now notice that's backwards, so we can always flip it. That's 16, that's 8, and change the sign. So let's see. From negative 4 to negative 3, we have a quarter of a circle. And this is another quarter of a circle. Okay. So the first quarter of a circle is going to be negative 1/4 pi, and its radius is 1. This would be a positive circle. 1/4 of pi, the radius is 3 squared. So I have, let's see, 8 minus negative 1/4 pi plus 9/4 pi. That would give me 8/4 of a pi, which is 2 pi. Now finding the derivative. The derivative of g prime, of g. Let's just start with taking the derivative. Well, we know how to take the derivative of 1/2 x squared. That's just going to be an x. The derivative of our new defined function, we're going to plug in x for t times the derivative of the inside. X plus f of x. So g prime of 3 is going to be 3 plus f of 3. And if I look at the graph, when x is 3, f is negative 3. So 3 plus a negative 3 is 0. G double prime. All right, so we have g prime is x plus f of x. G double prime is going to be 1 plus f prime. And we're going to evaluate that at 2. 1 plus f prime at 2. That's the slope when x is 2. So let's see. At 2, we're right here. What's the slope right there? Well, it's going, we could do the whole down 2 over 1. Down 2 over 1, down 2 over 1. That works. So 1 minus 2, which is negative 1. There's some practice problems on the back. We'll be going over questions on those on Monday. So have fun.